Thank you so much, Dirk, for allowing me this opportunity to share with colleagues from around the world and hosted by Chatham House. My role is really just to perhaps explain a little bit what we should and shouldn't expect from so-called model predictions. And the first thing I should say is that prediction is not the only function of models, and in fact, it should only be probably a minority of objectives should concern predictions. Models do a lot more things, and here I try to show you a little bit of what the concept of modeling is. So if you look at this picture of a butterfly, that's reality. And what modeling does is it tries to perhaps approximate reality. And one way of doing that visually is using pixels. Another way is to use contours. And you can see that both try to approximate reality, but they are not quite reality, and they're quite different from each other because they use different methods. Now, if you actually go up, you have greater complexity and therefore greater fidelity to reality, and less model distortion. Whereas if you have a simpler model, you will get much more distortion of reality. Now, sometimes what you get is you have a set of observations, so empirical data, and you get what you see in the middle. And what you try to do is to reconstruct reality from your set of parsimonious observations in real life. And model one gives you that. And then if you refine, and as you refine model one, it gives you this picture. Model two gives you approximately the same thing as model one on the first try, but then if you let it go on until the very end, you wouldn't realize that it gives you a completely different depiction of the supposed reality. Now, if you then take that sort of 35,000 feet view and look at specific application to infectious diseases, one of the first sort of modern modeling exercises was concerning HIV/AIDS. So there was a very famous, or rather infamous, paper published in JAMA back in 1990, looking at predicting the course of the HIV epidemic. And the authors here used essentially Farr's law. William Farr was a Victorian English scientist, and he basically said if you actually observe epidemics, they always come almost invariably in this bell shape. And essentially, mathematical or statistical, in this case, footwork, would allow you to then draw something like this. If you pay attention to the y-axis and then compare it to reality. This is by Tony Fauci back about 25, 26 years ago. And it's not a modeling paper. It just tells you the first 20-year history of the HIV/AIDS epidemic. And indeed, if you just look at cases and deaths of AIDS, not even HIV, you can see how wrong this initial Farr's law-based model really was. Fast forward to COVID-19, and if you actually look at a couple of papers here, one is from the Johns Hopkins Bloomberg School of Public Health, and the other is by Nick Jewell, published in Annals. Nick Jewell works in Cambridge. So if you actually look at two different models, one is by IHME, or the Institute of Health Metrics and Evaluation in Seattle, headed by Chris Murray, and then the Imperial College London model, headed by Neil Ferguson. If you actually look at their predictions for Italy and New York State, and you look at the training data, the prediction, which is yellow, and then the observed subsequently. So based on the red, they had the yellow, and then the blue is actually reality. You can see what a world of difference, because at least in the beginning, the IHME model was actually very much a Farr's law-based model, and that's why it was quite wrong. Whereas it was a much more nuanced and sophisticated transmission model that Imperial used, and that's why you see that things were actually much more truthful to reality for both Italy as well as New York State. So if you then take a step back and say, hey, what about flu data? And Google flu trends actually had a big boo-boo because it really didn't work very well. As you can see, Google really overestimated the peak by quite a few X's here back in 2013. And then if you actually look at these earlier studies, they were pretty good. But then when the Black Swan event came, didn't really work, which is when you really needed it to work. Similarly, dissections by John Brownstein from Harvard and company in PLOS computational biology, again, sort of tried to look at the circling-based type of CDC model versus the Google flu trends model. Is it really, when we hit the big data age, that we don't need theory anymore? Of course not. Big data just means really, really big garbage in, garbage out, unless you understand and really pay attention to the model structure. And there are a lot of people who have actually spoken or written about it already. Now, this comes to our work, which was actually done in the middle of January last year. It was really to try to answer the question, what might happen if no controls were put in place. This piece of work actually came out in The Lancet in the last week of January last year, predicting that we were going to get a pandemic. And of course we did. But how we did it was really looking at backwards inferring the size of the Wuhan initial cluster by the exported cases to Japan and to Thailand initially, and then using IATA or flight data to backwards infer the initial size of the outbreak, and then which spread to the rest of China in the country domestically through the Spring Festival related travel, which by the way is the largest annual human migration in the world. And what we showed also was in different cities in China, what it could be if no controls were done. And here we showed the blue bars were what actually happened. The red bars were our predictions. And the green bars is just using a different set of definitions for reality. And what you see is actually didn't work very well here in Changsha and Nanchang, as well as Chongqing. And what you find here is that that's because road traffic accounted for a larger proportion of human mobility. And that's why it really didn't work too well in these places, whereas it was actually very close in the rest of the country. As I said, our aim was not to predict precisely how many people were going to get infected, but rather to say, if you do nothing, you're going to get an absolute catastrophic result. Whereas if you reduce transmissibility by at least 50%, you are going to get this kind of result. And indeed, empirically, by the end of March, when you actually look at the Chinese numbers, you can tell that except for the original epicenter of Wuhan, they were able to, through basically a nationwide and within country lockdown between provinces and cities, that they really pushed the transmissibility reduction upwards of 75 or sometimes even 95%. Now, the second piece of work, again, about predictions is in Hong Kong. This came out very, very recently in Nature Communications. And it was really using our octopus card data, which is essentially capturing 95% of all mobility of the local population by various public transport means, and looking at deconvoluting these delay intervals so as to then backwards infer what the RT might become. And to cut a long story short, we found the sort of data stream that is most highly correlated with the RT stream historically, that is based on earlier data from the first quarter of last year. And then we nowcast and forecast it. And as you can see, moving from left to right, actually the nowcasting and the forecasting was pretty good. And that's actually what we relied on to tune our social distancing policies in Hong Kong. Finally, just let me thank key members of the team and also their own teams and our major funders for bringing to reality a lot of this work. Thank you.